Safe and sustainable engineering is not a review performed after the design is complete. It is the discipline of making better engineering decisions from the first day of the project to the final day of the asset. I want you to consider one uncomfortable question. When an incident occurs during construction, commissioning, operation, maintenance, or decommissioning, where did the failure actually begin? It may appear to begin in the field, but many failures start years earlier. They begin inside an unclear requirement, an unchecked assumption, a rushed calculation, an incomplete review, an unresolved interface, an uncontrolled design change, or a hazard that somebody recognized but nobody owned. That is why safe and sustainable engineering must be treated as an integrated engineering delivery process, not as a separate safety exercise. The objective is simple to state, but difficult to achieve. The asset must be safer to manufacture, safer to construct, safer to commission, safer to operate, safer to maintain, safer to modify, and safer to decommission. At the same time, it must remain technically compliant, economically viable, environmentally responsible, and practical for the people who will use it. This requires 3 connected engineering disciplines. The first is technical integrity. Technical integrity confirms that the design satisfies legislation, regulatory commitments, certification requirements, approved codes, engineering standards, customer requirements, and the established basis of design. It is the minimum foundation of a defensible engineering solution. The second discipline is safety in design. Safety in design goes beyond basic compliance. It asks whether hazards can be eliminated, substituted, isolated, or reduced through engineering decisions before people are exposed to them. The third discipline is sustainable design. Sustainable design evaluates how engineering decisions affect energy consumption, emissions, waste, water use, resource efficiency, ecology, communities, operating resilience, and long-term economic performance. These 3 disciplines are inseparable. You cannot achieve meaningful safety in design or sustainable design when technical integrity is weak. If requirements are unclear, calculations are unchecked, interfaces are unmanaged, and design changes are uncontrolled, then advanced risk studies will not rescue the project. Technical integrity is the foundation. Safety and sustainability are built upon it. The engineering process can be organized into 4 essential stages: alignment, planning, execution, and verification, followed by approval. The first stage is alignment. Before detailed engineering begins, you must understand what the customer expects, what legislation requires, what risks the organization is prepared to accept, and what outcomes the design is expected to deliver. Never assume that everybody has the same interpretation of words such as safe, sustainable, reliable, or acceptable. One stakeholder may believe that compliance with a code is sufficient. Another may expect inherently safer design, reduced emissions, remote operation, minimum maintenance exposure, or elimination of confined space entry. These expectations must be discussed and converted into clear engineering objectives. Alignment should establish safety goals, sustainability goals, applicable requirements, risk acceptance criteria, responsibilities, decision authorities, approval requirements, and the appropriate level of engineering rigor. Alignment should also expose contradictions early. The customer may request minimum capital cost while expecting maximum reliability. The schedule may demand immediate equipment selection while process data remains incomplete. Operations may require easy maintainability while the proposed layout provides no removal access. Construction may require modular installation while engineering has already fixed dimensions that make transportation impractical. These conflicts do not disappear because nobody documents them. They return later as redesign, delay, cost escalation, operational difficulty, or risk. Early alignment is not administration, it is risk prevention. The second stage is planning. Once the objectives are understood, the project must define how they will be delivered. The engineering plan should identify the applicable procedures, design reviews, safety studies, sustainability assessments, technical peer reviews, approval gates, responsibilities, resources, and schedule interfaces. The plan must answer practical questions. Which hazards must be studied? Which decisions require formal evaluation? When will process flow diagrams, piping and instrumentation diagrams, equipment layouts, and 3-dimensional models be reviewed? When will operations, maintenance, construction, procurement, and commissioning personnel contribute? Who owns each risk reduction action? Which records must be transferred into the next phase of the project? A plan that merely lists workshops is not enough. Timing determines value. A hazard and operability study conducted after equipment has been purchased may identify hazards, but it may no longer influence the design economically. A model review conducted after piping fabrication has started becomes a clash reporting exercise rather than an opportunity to optimize access, maintainability, and safety. A technical study creates value only when its findings can still change the design. Planning must therefore connect each study, review, and decision to actual engineering maturity. The correct analysis performed too late is still poor engineering. The third stage is execution. Execution begins with discipline definition. You must establish the scope, basis of design, design criteria, engineering assumptions, operating philosophies, deliverables, discipline interfaces, information requirements, specialist services, and software requirements. Ambiguity at this stage is dangerous because undefined inputs do not remain empty. Engineers fill them with assumptions, and different disciplines often fill them differently. Execution then requires competent people, controlled information, coordinated disciplines, checked deliverables, managed changes, and active treatment of risk. Every engineer and designer must understand the project context, not merely the task placed on their desk. A piping designer positioning a valve must understand access, operability, maintenance removal, lifting requirements, escape routes, drainage, exposure to process hazards, and the possibility of future modification. An instrumentation engineer selecting a measurement technology must understand failure modes, testing requirements, bypass control, environmental conditions, response time, and the consequence of an incorrect reading. An electrical engineer defining equipment locations must understand hazardous areas, ignition sources, emergency access, maintainability, environmental exposure, and future expansion. A process engineer defining inventories, temperatures, pressures, and operating envelopes must understand how those decisions affect containment, escalation, relief capacity, shutdown performance, and emergency response. A mechanical engineer selecting equipment must understand maintainability, lifting, inspection, vibration, containment, isolation, and long-term degradation. A civil or structural engineer must understand access, drainage, fire exposure, escape, dropped object risks, foundation behavior, and the consequences of structural failure. Safe engineering emerges when disciplines understand how their decisions interact. This is why discipline-specific communication is essential. Each discipline should receive a concise description of the project hazards, major accident scenarios, technical integrity concerns, safety goals, sustainability objectives, critical interfaces, required reviews, and discipline-specific risk reduction strategies. This information should not replace the project risk register. It should translate the risk register into practical design focus. A risk register that remains with the safety team is not controlling risk. A risk register becomes valuable only when its content changes calculations, specifications, layouts, equipment selections, operating philosophies, maintenance strategies, and procurement decisions. The register must remain active throughout the project. It should record the hazard, initiating cause, possible consequences, existing safeguards, level of risk, required risk reduction measures, responsible owner, required completion date, and evidence of closure. Do not confuse recording risk with managing risk. A long list of open actions may prove that a workshop occurred. It does not prove that the design became safer. Risk reduction measures must be implemented while the design still has flexibility. Every delayed action becomes more expensive, more disruptive, and more likely to be weakened, deferred, or rejected. The hierarchy of controls must guide risk reduction. The strongest control is elimination. Can you remove the hazard entirely? Can the process condition, material, equipment arrangement, operating method, or maintenance requirement be redesigned so that the exposure no longer exists? The next level is substitution. Can a hazardous material, technology, or activity be replaced by one with lower potential for injury, environmental damage, or asset loss? Then comes prevention through engineered controls. Can you reduce inventory, lower pressure, reduce temperature, segregate equipment, isolate energy, automate hazardous tasks, improve containment, or reduce dependence on human intervention? Below engineered controls are administrative measures such as procedures, permits, signs, training, and supervision. At the lowest level is personal protective equipment. Personal protective equipment may be necessary, but it should never become the preferred answer to a hazard that could have been removed through design. The later a hazard is identified, the further down the hierarchy you are usually forced to operate. During concept development, you may eliminate the hazard. During detailed engineering, you may only be able to install a guard, barrier, or interlock. During operation, you may be left writing a procedure and asking people to be more careful. That is the cost of late thinking. Safety in design must also consider the complete asset lifecycle. You are not designing only for stable operation. You are designing for manufacturing, transport, construction, installation, commissioning, startup, normal operation, abnormal operation, emergency conditions, inspection, testing, cleaning, maintenance, modification, shutdown, decommissioning, abandonment, and disposal. Foreseeable misuse must also be considered. People will work under time pressure. Equipment will fail. Instruments will drift. Valves will be left in the wrong position. Temporary hoses will be installed. Access routes may become obstructed. Alarms may be ignored. Procedures may be misunderstood. Good design does not assume perfect human behavior. Good design anticipates realistic human behavior and reduces the probability and consequence of error. Human factors and ergonomics therefore belong inside engineering. Can the operator clearly see the indication? Can the maintainer reach the component? Can heavy equipment be removed safely? Are displays and controls understandable? Are alarms prioritized? Can isolation be positively verified? Does the layout support escape and emergency response? Can the task be performed without excessive force, awkward posture, or unnecessary exposure? A technically functional system that is difficult to operate or maintain safely is not a successful design. Detailed studies and assessments must support decision-making, not merely certify work that is already complete. Hazard identification studies, hazard and operability studies, functional safety assessments, quantitative risk assessments, human factors reviews, constructability reviews, maintainability reviews, environmental assessments, and technical peer reviews should be selected according to project complexity, maturity, and risk. Not every project requires the same level of formality. The process must be scalable, but the underlying principles cannot disappear. Small projects still require competent decisions, clear assumptions, hazard awareness, design coordination, change control, and verification. Familiar technology may reduce uncertainty, but familiarity must never become complacency. Decision management is another critical part of safe and sustainable engineering. Early decisions shape the asset for decades. A lower-cost equipment arrangement may increase maintenance exposure. A reduced spare equipment philosophy may lower capital cost while increasing production risk. A compact layout may reduce footprint while worsening access, congestion, fire escalation, and emergency response. A cheaper material may reduce initial cost while increasing corrosion, inspection, and replacement requirements. Engineering decisions must therefore be open, traceable, technically justified, and appropriate to the project context. Important decisions should record the options considered, evaluation criteria, technical consequences, safety effects, sustainability effects, life cycle costs, stakeholder input, residual risks, and final justification. This is not unnecessary paperwork. It protects the project from repeating old arguments, losing technical reasoning, or discovering later that nobody remembers why a critical choice was made. Technical integrity must remain visible throughout execution. It depends on competent personnel, a clear basis of design, controlled documents, checked calculations, interdisciplinary reviews, discipline change management, technical peer reviews, procurement support, construction support, lessons learned, and formal approval. Several conditions repeatedly threaten technical integrity. These include fast-track schedules, poor project definition, missing information, ambiguous standards, insufficient resources, inexperienced personnel, uncontrolled changes, fragmented responsibilities, and communication barriers. These conditions must be treated as project risks. A compressed schedule does not remove engineering obligations. It increases the need for prioritization, interface control, and independent verification. When information is incomplete, assumptions must be documented, approved, monitored, and replaced when confirmed data becomes available. When standards conflict, The governing requirement must be resolved rather than left to personal interpretation. When resources are inadequate, management must understand which assurance activities are being compromised and what risk is being created. The fourth stage is verification and approval. Completion is not the same as assurance. Before a design moves into the next phase, the project must verify that the planned processes were implemented and that the intended outcomes were achieved. Verification should confirm that lifecycle hazards were identified, risk reduction measures were closed, technical decisions were properly informed, reviews were completed, technical integrity requirements were satisfied, and residual risks were transferred to the people who will construct, commission, operate, maintain, or decommission the asset. A useful verification system distinguishes between failure, provisional acceptance, and full acceptance. Failure means that significant work remains or that important risks are not adequately understood or controlled. Provisional acceptance means that the design substantially meets its objectives but contains clearly defined exceptions that are documented, accepted, and prevented from compromising technical integrity. Full acceptance means that the design meets or exceeds the agreed objectives, actions are closed, and residual risks are understood and justified. Verification must examine evidence, not confidence. Statements such as "the team discussed it" or "the design should be acceptable" are not evidence. Evidence includes approved calculations, completed reviews, closed actions, updated risk registers, controlled drawings, peer review records, design change records, and documented handover information. Leadership is what makes this system work. The project manager must establish expectations, secure resources, and maintain alignment. The engineering manager must integrate the process into engineering execution, schedule the required studies, and ensure that actions are closed. Safety and environmental leaders must facilitate risk activities that genuinely influence the design. Discipline leads must translate project risks into discipline decisions, reviews, and deliverables. Engineers and designers must understand the hazards connected to their work, raise concerns, and comply with the agreed project requirements. Responsibility cannot be transferred to the safety department. Safety specialists can facilitate studies, challenge assumptions, and provide specialist analysis. They do not design the asset. Engineers and designers control the technical choices that create, remove, or reduce hazards. That is the raw truth of engineering accountability. You do not achieve safe and sustainable engineering through slogans, workshops, or approval stamps. You achieve it when risk information changes the design. You achieve it when a hazard is eliminated before procurement. You achieve it when a maintenance task no longer requires unnecessary exposure. You achieve it when a decision reflects lifecycle value rather than only immediate cost. You achieve it when every discipline understands the consequences of its choices. You achieve it when technical integrity, human safety, environmental responsibility, and operational reality are considered together. The real measure of engineering is not whether the drawings were issued on schedule. The real measure is whether the asset can be constructed, operated, maintained, modified, and retired without transferring avoidable risk to somebody who was never present when the design decisions were made. That is what safe and sustainable engineering must deliver. If this perspective adds value to your engineering practice, like, share, and subscribe to the channel. Continue exploring these engineering design and project execution podcasts and bring these principles into your next design review, engineering decision, and project risk discussion.